All right, hi everybody. So this was a something that people asked about, which was Chapter 7, number 30 here, and I remember too it was a big issue last year too. So I'm gonna do this. So okay, here we go. It says, suppose the ski patrol lowers a rescue sled and victim, having a total mass of 90 kilograms down a 60-degree slope. Don't worry about that one. At constant speed. So if it's at constant speed, that means I know the acceleration has to be 0. That's something you want to pick up on. It says as shown below, so you can see right here. The coefficient of friction between the sled and the snow is 0.1. How much work is done by friction as the sled moves 30 meters along the hill? So I know the displacement is 30 meters. So the displacement is down like that. So it's being dragged down. They give me some of the forces, and really these are just the forces that are going to matter when it comes to the work done. But I drew them as a free body diagram right here. So I got the normal force perpendicular to the surface, tension force like that, and then the friction force like that. And then I also got the weight going down. So I flipped my axes. The displacement is going like this. I flipped my axes. So I got the y pointing perpendicular to the surface, x pointing parallel to the surface. So this means then the only vector I have to split up is the weight. So here I got mg cosine and alpha. I know it's strange I'm calling it alpha, not theta. There's a reason for it, and I'll show it to you later, where alpha is 60 degrees. So this 60-degree angle, which is this angle, and this angle is what I'm calling alpha right now. And so then the horizontal component then is going to be mg sine theta. All right, there we go. So the first thing they're asking me to calculate is how much work is done by the friction force as the sled moves 30 meters along the hill. So this, to calculate the work, well, it's just the magnitude of the force. So that's going to be the magnitude of the friction force multiplied by the displacement multiplied by cosine of, now I'm using theta. And this is where I want to be careful. This is why I'm using alpha for this one, because theta is the angle in this general formula, this general equation. Theta is always the angle between the force and the displacement. In this case, it'd be the frictional force and the displacement. All right, so let's see. So in order to do this, well, I got way, okay. So it's going to be, well, let's see. I got the displacement. That's going to be it's going to be 30 meters. So I got to get the frictional force. So I don't know what the frictional force is, and to do this, I'm going to use the fact that the frictional force, the friction force is the coefficient of kinetic friction multiplied by the normal force. And then to get the normal force, I'm going to use F net equals ma. In the vertical direction, I think. So in the vertical direction, F net, so I got normal force minus mg cosine theta. So it's going to be the normal force minus mg cosine, not theta, alpha, equals, and then the acceleration in the vertical direction is going to be 0. So that tells me then that the normal force is equal to mg cosine alpha. And then I can basically take that and plug that in here. And that'll give me the frictional force. So my friction force is going to equal mu k times mg cosine alpha. All right, there's that, and then now all that is going to go in here. Now all that is going to go in there. So this is going to be then the work done by the frictional force is equal to mu k mg cosine alpha multiplied by the displacement multiplied by cosine of the angle between the frictional force and the displacement. So now I can just plug in all my things that I want to find out. So the coefficient of friction is 0.1. The mass is 90. G is 10. Cosine of alpha is 60 degrees. Displacement is 30. Cosine of, what's the angle between, so let's see. The frictional force is pointing this way, and the displacement is pointing this way. So if I pitted those two against one another, I would get an angle of 180 degrees because they're both pointing in opposite directions. So that means this is going to be cosine of 180. So the work done by the frictional force then is, oh, I gotta get my phone. So that's going to be, 0.1 times 10 is 1. So I got cosine of 60, I'm pretty sure is a half. So I got cosine of 60 times 90 times 30. And then the cosine of 180 is -1. So this is going to end up being, and I'm rounding to two significant figures for a very specific reason. So I'm going to say negative 1,400 joules. So there we go. There's the work done by the frictional force. So it's negative 1,400 joules. I'm rounding to two significant figures. Okay. Next up then, so there's that one. So part B. Part B is asking what's the work done by the rope. So that's going to be the tension force right there. So the work done by the tension force, so let's throw it over here. Part B, work done by the tension force. That's going to be the magnitude of the tension force itself, multiplied by the magnitude of the displacement, multiplied by cosine of the angle between these two vectors. All right, so the work done by the tension force. Well, to get the tension, so again, I know the displacement. I can find out the angle. That's going to be no big deal. But to get the tension force, I'm going to need to go back to F net equals ma. It's still there. It still works. It's still good. So F net equals ma. This is now in the horizontal direction. I've got the mg, the x component of the weight here, and then I got these two forces, the tension force and the friction force, both pointing to the right. So for F net, I'm going to say the tension force plus the friction force minus mg sine of alpha equals, and then again, it's moving with a constant speed, so the acceleration has to be 0. So, all right, I'll say the acceleration is 0. So let's see. So friction force, I can just use what I had over here. I can just use what I had over here to find out what the friction force is. So the friction force is going to be, let's see. What do I got all that? I'm good then. So yeah, the tension force is going to be, so plus the friction force, which is mu k mg cosine alpha minus mg sine alpha equals 0. Now I'm going to isolate the tension force. So it's going to be the tension force equals mg sine alpha minus mu k mg cosine alpha. Mg is the similar term for both of them, so I'm just going to factor out the mg to hopefully make it an easier calculation. So it's going to be mg sine alpha minus mu k cosine alpha. And now I can plug all this now is going to go into here, is going to go into that equation. So this is going to be, let's see if I can, this was all in the, should probably make all this red. So make all that red. There we go. Because this is all in the x direction. And I try to maintain consistency there. So now the work done by the tension force is going to be the tension force itself, right? The magnitude of the tension force itself, right there. So it's going to be mg sine alpha minus mu k cosine alpha. The multiplied by the magnitude of the displacement, multiplied by cosine of the angle between the tension force and the displacement vector. I think now I can just plug in values here. So the work done by the tension force is going to be mg. Let's see, do that. Let's do this. So it's going to be the mass is 90, g is 10. Sine of the angle is 60. Minus mu k is 0.1 times cosine of 60. And then the displacement again is 30. And then cosine of the angle between the tension force. Again, this is similar to the friction force. The tension force points to the right. The displacement points to the left. They're opposite each other, so the angle is going to be 180 degrees. All right, now I'm getting this one. This one's going to be a little more complicated, but I can still do it. I typically, I'm going to first calculate what's over here. So I got cosine 60 times 0.1, and then sine 60 minus that. So minus 0.05 is what I got for 0.1 times cosine 60. Multiplied by 90 times 10. And then multiplied by 30. And then multiplied by cosine of 180, which is -1. So that's going to give me, I'm getting negative, so work done by the tension force is negative 22,000 joules there. So that's the work done by the tension force. Next up, they're asking what's the work done by the gravitational force. All right, let's do this one. So this is part C. Work done by the gravitational force, you can probably guess, right? It's the same idea. So we got the gravitational force itself, the magnitude though we want, multiplied by the displacement, multiplied by cosine of the angle between those two vectors. So that's going to be the work done by the gravitational force is, do I got all this? Yes, I do. Yep, yes, I do. So I'll just plug all this in then. So it's going to be the mass, which is 90, multiplied by g, which is 10, delta x is 30, cosine, ooh, what's the angle? It's the angle between the weight vector, the actual weight vector, by the way, the actual weight and the displacement. So, okay, what's the angle between, oh, here's the weight. So here's the displacement vector. The displacement vector is pointing in the same direction as the x component of the weight. So that's this right here. So what's the angle between the actual weight and this displacement vector right here? The angle is this right here. I'll do it in green. So I'll make it double, and this is theta for that, right? So what is theta? How can I get that? Okay, well, let's see. I know these are got to be perpendicular to each other because they're component vectors. Component vectors are always perpendicular to each other. If this then alpha is 60 degrees, that means then theta has got to be 30 degrees. So theta in this case is 30 degrees for this particular thing here. So yeah, so all right, that's going to be then 30 degrees. All right, now I can calculate all this. That's going to be 900, so 90 times 10 times 30 times cosine 30. And I'm getting 23,400 joules. There you go. So there's that. Yeah, I think that's right. And it's positive. It's positive. So the work done is positive because the weight is pointing, or you know, part of the weight is pointing in the same direction as the displacement. Now, you might want it to have, you know, like done this, right? Done this, the x component, and then multiplied it by this. You could totally have done that. Just be careful with your angles and all that kind of stuff. I'm not going to go into it in this video, but you're going to get the same answer. Okay, so the last then question says, what's the net work done, right? What's the total work done? Yeah, what's the total work done? The total work done. Couple ways I'm going to do. I will do this two ways. The first way is, well, net work. Well, that would be the magnitude of the net force multiplied by the displacement of the object, multiplied by cosine of theta. Well, the magnitude of the net force, the acceleration is 0, right? The acceleration is 0. So, you know, F net equals ma. So if the acceleration is 0, then that means F net is 0. So basically we got work net is going to be 0 multiplied by the displacement, which is 30, multiplied by cosine of, well, there is no really angle between these two things because So just say cosine of theta, it doesn't matter, but 0 times all this, it's going to tell me that the net work is going to be 0. Lastly, one of the reasons I rounded the way I did is because of what I'm about to do next. So the other way you can calculate the net work, and all of this is legit, is to basically say, well, it's the total work done by all the forces. So we got the work done by the frictional force plus the work done by the tension force plus the work done by the gravitational force, and I could even add the work done by the normal force. So the work done by the frictional force was negative 1400 joules, plus the work done by the tension force, that was negative 22,000 joules, plus the work done by the gravitational force, we found just there, 23,400 joules, plus the work done by the normal force. Well, I could calculate all that out, but I would want to look at here. The normal force is pointing that way, directly in the y direction, which is perpendicular to the displacement. So if it's perpendicular to the displacement, the normal force is not going to do any work. In fact, rarely does the normal force ever do any work. So the work done by the normal force is 0. So now I got negative 1,400 plus negative 22,000 plus 23,400, and that's going to all add up to 0. So the work net is 0 as well. So there you go. Yeah, hope that helped. And all right, see you later. Bye.